credit lecture over 4.2 and 4.3, just the parts that are over the Rolle's theorem and the mean value theorem. This is not 100% essential. I mean, it is important, but it's not essential to the course, so we're just going to do it as extra credit, so those of you who want some have an opportunity to get it. So what Rolle's theorem says is this: if f is continuous on closed interval AB and differentiable on open interval AB, and if f of A equals f of B, so that means you've got an interval where the y values at the two endpoints are equal, then there exists some c, that's an x value, in between A and B such that f prime of c equals 0. So what that's saying is if you've got a continuous function that's also differentiable where the two y values on the endpoints are equivalent, then there's some place in between where the derivative is 0. And it's really illustrated nicely by this diagram here. So here you've got an endpoint A and endpoint B, and notice those y values have to be equal. Well, if it's continuous and differentiable, that means it's smooth. So that means there has to be at least one value of x, in this case it's right there, where the derivative equals 0, and that's somewhere in between A and B. It could also look more like this one. For some reason this thing isn't working here, but so I can't move that red line. But you can imagine, okay, there's a place right there, just where my mouse is, where the derivative is 0, and a place right here where the derivative is 0. So if A was, say, equal to 0 right there, let's call that 0, and let's say the other endpoint B was maybe 5. Oh, maybe it is working. Here we go. So there's two places actually in between 0 and 5. One is right about in there, a little less than 1, where the derivative is 0. And the other place is kind of right in there somewhere. It's hard to get it exactly, but so there it is, about 0.88 and about 3.79. So there could be more than one place where the derivative is 0, but all Rolle's theorem says is there is at least one x value where the derivative is 0 if those two y values at the endpoints are equal. You could also make it so, like in this example, the two y values could both, oh, it won't let me go that far. I was going to say where they're both equal to, like, I could make A equal to 2 and B equal to 5. They'd both be equal to 0 there. And then there would only be one x value in between them where the derivative is 0. Okay, so why does it have to be both continuous and differentiable? It's easily illustrated by these two diagrams right here. If the function is not continuous, well, here's an example where the y values at the two endpoints are equal. They're both 0 in this case, but there's no horizontal tangent. Or if it's not differentiable, if you have a sharp point, you could have some case like this where, sure, the y values are equal, but there's no horizontal tangent. Okay, so let's find an interval on which Rolle's theorem applies to f of x equals x cubed minus 7x squared plus 10x, and then we'll find all the points on that interval at which f prime of c equals 0. Now there's infinitely many correct answers for this problem because we're just finding an interval on which Rolle's theorem applies. So that means any interval where f of a and f of b are both equal. For simplicity, I'm gonna choose a and b so that f of a and f of b are both equal to 0, because that just seems like an easy way to solve it. If I let y equals 0, this equation is pretty easy to solve because we can factor out an x from all three terms. That would leave us with x squared minus 7x plus 10. Let's see, looks like that's going to factor. Let's see if this works. Right, yeah, that should work. Factors. So there's three x values at which the function equals 0. Now I could have set it equal to 1 and solved, or I could have set it equal to 2 or 3.5 or pi. I mean, we could set this number equal to anything. We're just trying to find x values at which the y values are all the same. So 0 just seemed like a simple choice. Okay, but you could do anything for that number right there. So this means f of 0, f of 2, and f of 5 are all equal to 0, so it doesn't really matter what we let a and b. Let's just let's just choose A to be 0 and B to be, let's do the bigger one, 5, because that gives me more places where the derivative is going to equal 0. So there's my interval. So now by Rolle's theorem, there definitely exists some x value in between 0 and 5, or you could call it c, where f prime of c equals 0. So let's find that. And actually there should be one in between 0 and 2, right? And then another one, at least one more, between 2 and 5, because I got all three of those as places where the function is 0. So let's take the derivative. F, so f prime is 3x squared minus 14x plus 10. Somewhere that equals 0. And let's see if this thing factors. We've got 3x, x, say 10, we could maybe split up into 5 and 2. That I don't think is going to work, because if I put the 5 here and the 2 here, that would give me 15x and 2x. No way do we get 14x out of that. Or we could do maybe 10 and 1, actually. If we put a 10 here and a 1 there, that's 3x and 10x. No, still not 14. Reversing them isn't going to help. I'm not sure that that thing factors. Let's use the quadratic formula. So negative b is 14 plus or minus the square root of b squared minus 4ac all over 2a. So we need 14 squared minus, that's going to be 120. I'm not sure if you can see my calculator on this or not, but I'm doing 14 squared minus 120 is square root of 76. So it gives us 14 plus or minus the square root of 76 all over 6. In order to tell where these x values lie and whether or not they're in this interval, we're going to have to approximate, because I can't tell from looking at it what that value is. You could figure it out, but we'll just approximate. So we're going to do 14 plus the square root of 76 all divided by 6 is about 3.786. Or if we do 14 minus the square root of 76 all divided by 6, that's about 0.8804. Let's go with 0.880. So yeah, we've got one x value here that's between 0 and 2 and another one that's between 2 and 5, which is exactly what we thought. So those x values are these, guaranteed to exist by Rolle's theorem. Okay, this next example is it's really something that you would do more if you're interested in math. Okay, I'm going to show you a proof, and I want you to follow through the logic. This is kind of neat. Use Rolle's theorem to prove that this function has at most one real root. So I'm going to do what's called a proof by contradiction, and that means you actually start by assuming that the opposite is true, and then we'll get something that is obviously totally false, which means that our assumption must have been false so that the thing is true. So that's called a proof by contradiction, and I'll say that again as we go. So we're going to start by supposing that f has more than one real root, because that's the opposite of it having at most one real root. Well, a root means a place where the function equals 0. So if f has more than one real root, then that means there exists at least two values. So let's just go with an a and a b, such that f of a and f of b both equal 0. Well, that gives me two x values where their y value is the same. The y value at both of those x values is 0. So by Rolle's theorem, that guarantees us that there is a c somewhere in between a and b, such that the derivative at C is equal to 0. So let's just keep going with this logic and try to find that C value where the derivative is 0. So let's take the derivative. We get 3x squared minus 2x plus 2. So this derivative has to equal 0 somewhere, so let's see. I don't think that's going to factor. So let's just jump to the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So we get 2 plus or minus the square root of 4 minus 24, negative 20, all over 6. Well, obviously that's not a real value, right? Those are imaginary numbers. So there are no such x's, right? But there are no values of x where the derivative is 0. But we were guaranteed to have a value of x where the derivative is 0. So this must mean that our original assumption was false, that f has more than one real root. So that was false. Therefore, f must have at most one real root. It's kind of a roundabout way of doing it, but it works. It's a valid proof because logically it's very sound. So that, I hope you can just follow through the logic on that. That one's kind of fun. Okay, next let's look at the mean value theorem. This is just an extension of Rolle's theorem. So what the mean value theorem says is if you have an a and a b where they don't necessarily have to have equal y values. So a and b could be anything. So I'm going to do it like that. Let's make a here and b there. What the mean value theorem says is that there exists some point in between a, b where the slope f prime of c is equal to the slope of the secant line through a and b. So if you take any continuous differentiable function and you have two x values, you can find the slope of the secant line that goes through those two x values. What the mean value theorem says is that there definitely exists some c, in this case it's right about there, where the slope of that tangent line at c, f prime of c, is equal to the slope of the secant line through those 2 points. Okay, writing it out, that means if f is continuous on some closed interval ab and differentiable on the open interval ab, then there exists a c somewhere, at least one c, somewhere in the interval from a to b, such that f prime of c, the slope of the tangent line, equals the slope of the secant line through a and b. More easily illustrated through the diagram. You should probably draw that than through the writing. Okay, so and I know I'm jumping around kind of quick, but you guys can pause this video. Okay, so we could make b be somewhere out here, right? Then in this example, there would actually be two such c's. One is it's hard to get, right about in there. Those lines are parallel, and the other one looks like it would be right about in there. Yep, where the lines are parallel. Okay, so we're going to determine, let's do an example, we're going to determine whether this function f of x equals 2x cubed minus 3x plus 1 satisfies the conditions of the mean value theorem on the interval from -2 to 2. If it does, then we're going to find the point or points that are guaranteed to exist by the theorem. So, well, yes, it is continuous and differentiable, so that's pretty obvious because it's a cubic polynomial. So, mean value theorem does apply. So, let's find the points guaranteed to exist by the theorem on that interval. So, we need the slope of the secant line through those 2 points. of the line through -2, comma, let's just go ahead and find that y value. -2 cubed is -8, times 2 is -16, plus 6 is -10, plus 1 is -9, I think, is that right? And the other point is 2, comma, 16 minus 6 is 10, plus 1 is 11. So I'm going to double check that real quick. Yeah, I think that's right. Okay, so slope of the secant line through those 2 points, and you might even write f of 2 minus f of -2 over 2 minus -2 is f of 2 is 11 minus f of -2 is -9 over 4. So I'm getting 20 over 4, or 5, is the slope of the secant line through those 2 points. So there should be some point in between -2 and 2 where the slope of the tangent line equals 5. So let's find it. F prime of x is 6x squared minus 3. Somewhere that equals 5. So 6x squared equals 8. So x squared is 8/6 is 4/3. So x is plus or minus the square root of 4/3. It's 2 over root 3. Let's roughly approximate those. 2 over root 3 is about 1.155. Plus or minus 1.155, I think I said. Yeah. Which is, those two numbers are between -2 and 2. So there's actually 2 x values in between -2 and 2, where the tangent line is 5, which is the slope of the secant line through those 2 points. Okay, that's it for Rolle's theorem and mean value theorem. If you do the homework on this section, there's only 4 problems, and to make it simple, we'll just count each problem as 1 point. That'll add on to your total point value, so it's kind of like adding 4 points to a test or something. And that'll just be for extra credit. It's not going to show up as extra credit in your grade on WebAssign, but I'll make sure that I do it right through Blackboard when I go and import your grades.